Welcome to a basic introduction to mechanical ventilation. This is chapter 1.4, VQ mismatch.
Now, the VQ ratio is something you hear referred to commonly throughout these lectures, both during the study material in the book and also during lectures. And I just want to quickly go over what exactly a VQ ratio is and what that means. The VQ ratio is essentially a measure of the efficiency of respiration. The V in VQ stands for ventilation. Seems fairly obvious. There's V equals ventilation, easy to remember. And this refers to the air that's in the alveoli. Now, Q is not as obvious. Q is a physiological abbreviation for perfusion, and not just any perfusion. This is perfusion that has to be blood that's in contact with the alveoli itself. Under ideal circumstances, 1 liter of air contains approximately 210 milliliters of oxygen. Hint, this is where the FiO2 of 0.21 comes from. On the other hand, 1 liter of blood can hold about 200 milliliters of oxygen in the hemoglobin and dissolved in the plasma. Therefore, in an ideal lung, the VQ ratio is about 1. In reality, things are a little bit different, however. The average minute ventilation is 6 liters per minute, which translates into 4.2 liters per minute of effective ventilation that's in the alveoli and available for gas exchange. Cardiac output is approximately 5 liters per minute on average, which means that under the normal circumstances, the best we can do for a VQ match is 4.2 divided by 5, which gives us a ratio of 0.84. So even in normal circumstances, we don't have a complete VQ match, and ventilation and perfusion aren't really as efficient as they could possibly be. To further complicate things, we have to consider what the real lungs are like when a person is sitting upright. When standing, there is a mismatch of ventilation and perfusion that occurs naturally because of the influences of gravity. When you look at the top of the lungs, you can see that there's a very poor perfusion because blood is not under a lot of pressure coming out of the right ventricle and so doesn't flow as quickly or as well into the top parts of the lung and tends to want to preferentially go to the base of the lungs. On the other hand, however, because the lungs are being pulled down by the weight of gravity, the top of the lung is always completely open and always available for gas exchange. So at the top of the lungs, the alveoli look like this. You can see lots of ventilation, but not as much perfusion, and so in this region of the lung, the VQ ratio is actually very high. Now, when you take the converse of that at the base, the lung is actually being crushed by its own weight, and although there's a lot of blood flow going into that area because of the effects of gravity, the amount of ventilation is low because in those areas of the lung may not actually be participating in gas exchange because they're not being opened by the force of respiration. So in this area of the lungs, ventilation is low and the perfusion is high. And in this case then, the VQ ratio is low. The alveoli in this section of the lungs would look like this. So from the top of the lungs to the bottom of the lungs, there's a gradient of VQ ratios going from a high VQ ratio at the top to a low VQ ratio at the bottom. And this interplay between the different VQ ratios throughout the lungs gives us the average VQ ratio that we normally see of approximately 0.8. This is relevant for clinicians because alterations in VQ matching by changes in the patient position can have an impact on oxygenation and ventilation